Now that you've seen well-ordering principle, you may be wondering, why do I keep saying that this is useful to prove interesting things in mathematics? So far, we've done just a simple example, which doesn't really seem to be an interesting theorem of mathematics. So what can you prove using something like a well-ordering principle? One very interesting thing that you could prove using well-ordering, and this was done by Euclid, well, at least this was presented by Euclid in 300 BC in his Elements, is the theorem that there are infinitely many prime numbers. So this is, by the way, the same Euclid that did axioms of geometry, well, geometry as we know it, and he also did a lot of prime number theory, in particular that algorithm for computing greatest common divisor that you will see in your algorithm course is due to Euclid. But one really cool thing that was in his famous Elements is the proof that there are infinitely many prime numbers. So just to fix some notation, just to remind you the actual definition, a natural number is prime if it's only divisible by itself and by 1. And yeah, you could write it as a formula. We will just write prime of x to mean that this formula is true. And what do we mean to say that there are infinitely many? This is a more interesting thing to represent in logic. We could say that there are infinitely many of some numbers if no matter what number I give you, you could always give me a bigger one. That's the definition we are going to use here. So we will say that no matter what number, what prime number you give me, I could always give you another number which is prime and which is bigger. So let's prove it. So we'll do a proof by contradiction. We will assume that there is a largest possible prime, that there is nothing beyond it, and show that things go wrong, that this is not possible. So suppose, for sake of contradiction, that indeed there is a largest possible prime number. Let's call that number n. So that's a universal instantiation of the negation of the theorem statement. Now let's look at the following number. Let's multiply together all the numbers from 2 all the way up to n and add 1 to that number. Similarly, you could multiply all the primes starting from 2 and all the way to n. The proof wouldn't change. So now let's look at that number, which we'll call capital N, not to be confused with natural numbers. It's a different capital N. And now let's consider two cases. First case is that this number capital N is a prime number itself. In this case we are done because we found a number which is bigger than our original number, because the product from 2 to n is at least n itself. Well, if n is equal to 2, then it's n, and we add 1 to it to get n, so we get a bigger number. So in this case we are done already, got a contradiction. Now we need to consider the case when we got this new number and it's not a prime. Let's see what happens then. So now let's look at the interesting case. That is the case when that capital N number, which is the product of all numbers up to and including that little n, which was the biggest prime number that we are trying to prove is not the biggest prime number. So capital N is a product of everything up to then plus 1. And the second case, the more interesting case, was to look at the situation when this capital N is not a prime number. So what it means to be not a prime number? Well, it has some divisors. So now is where the well-ordering principle comes in. So just to remind you, the well-ordering principle says that any non-empty subset of natural numbers contains the smallest element. So what will be the subset of natural numbers in our case? Well, let's take all the numbers that divide capital N that are not 1 and not capital N itself. So S will be the set of all divisors of capital N. And by the well-ordered principle, there will be the smallest number greater than 1 that divides capital N, provided N is not prime. So, what can such K0 be? Can it be less than little n? Well, the way we constructed capital N is we took a product of all the numbers up to and including little n and added 1 to it. So no matter which of those numbers from 2 to little n you try to divide capital N by, you will get the remainder of 1, just by the way we built that number. So that means that K0 is not divisible by any number itself smaller than little n, and K0 itself is strictly greater than little n. And that means that K0 itself must be a prime. But wait a moment, so we just found a prime which is greater than little n. That's because everything that's less than little n has a remainder 1 when we try to divide capital N by it. And K0 is the smallest factor of n, so K0 might be a prime. So we've constructed in case 2 as well as in the case 1 a prime number that's strictly greater than this number that somebody was trying to convince us was the biggest prime, little n. By existential generalization, in this case also there is a prime number which is greater than little n. So we showed that in both cases of capital N being prime and not being prime, there is a number that's greater than little n, and that's prime. And there are no more cases. Capital N can only be prime or not prime. So that means that in every possible case, we show that there exists a number which is greater than n, and that's prime, which is exactly what we wanted to show. And since we assume nothing about the little n, except for it being a prime, we can now use universal generalization to conclude that for every x which is prime, there exists a greater number y which is also prime. And this is it for proof of the theorem that there are infinitely many prime. The theorem that first appears, as far as we know, in Euclid's Elements from 300 BC.